You ever wonder if one tiny little number could be, I don't know, silently wrecking your entire experiment? Well, that's what we're talking about today, the pH meter. It's one of those devices that's absolutely critical, but almost everyone misunderstands it. Stick around, and I promise you, you're going to see this thing in a completely new light. So, you look at this thing, right? It just looks like another piece of lab gear. But honestly, this little guy is probably responsible for more failed experiments than you can even imagine. And why is that? It's because we all treat it like it's a simple thermometer. And let me tell you, that is $1 million mistake. I mean, just think about it for a second. We're talking months of work, right? Super expensive reagents, maybe even some groundbreaking ideas, and all of it, every last bit, is resting on one single number. And if that number is off, everything that comes after it is built on a house of cards. It's a lie. Honestly, the stakes just don't get much higher than that.
All right, so what is this huge mistake we're all making? It's something that feels so simple, so intuitive, but it's completely wrong. And it can lead to total disaster. Let's get into it.
Okay, so here's the trap pretty much everyone falls into. You see the probe, you see the digital screen, and your brain just goes, oh, okay, it's basically a fancy thermometer. You just dip it in, get a number, and you're done. Simple, right? But what if I told you that that simple, easy action is actually destroying your data?
And that is what makes it so dangerous. Because the number that pops up on the screen, it looks totally fine. It looks right. So you'd have no idea that your results are completely, utterly unreliable. It's like a silent killer of good science.
So to fix this, we've got to do a complete mental reboot. We need to just erase that thermometer analogy from our brains. From this moment on, I want you to think of a pH meter for what it actually is. A super, super sensitive voltmeter. It's not measuring heat at all. It's measuring a tiny, tiny electrical charge.
So what in the world does high impedance even mean? Well, think of it like this. Imagine trying to measure the air pressure inside a balloon, but you can't let even a tiny puff of air escape. That's what this voltmeter does. It's so sensitive it can measure that teensy little voltage in your sample without messing with it at all. And then it uses this really clever bit of math, the Nernst equation, to turn that voltage reading into the pH number we all need. Okay, so how does it work? Well, the magic really happens right here, on this amazing little glass bulb at the end of the probe. You see, it's coated in this special gel layer, and you can think of that gel as being like a magnet for hydrogen ions. The more of those little H plus ions that stick to it, the higher the voltage goes. But, and this is a huge but, here's the catch. If that gel layer gets dirty, or if it dries out, it's like you've wrapped the magnet in a thick layer of plastic wrap. Nothing can stick to it anymore. The ion exchange just stops. The voltage reading is totally wrong, and your pH number is completely meaningless. And that right there is why cleaning and storing this thing correctly isn't just a suggestion, it's absolutely non-negotiable. Okay, so we've peeked under the hood. We get the science now, right? It's time to put all that knowledge into practice. And listen, this isn't just a random list of tips I found online. This is the real deal, the expert's protocol for getting a perfect reading every single time. All right, first up, let's talk about this little face on the screen, the Senso face. I want you to think of this as your probe's own personal health report. A little smiley face? Awesome. It means your probe is healthy, happy, and in peak condition. But if you see that sad face, well, that's your probe literally crying out for help. It's telling you, hey, I'm not feeling so great, and my readings, yeah, you probably can't trust them. Ignoring that sad face is just like putting a piece of tape over the check engine light in your car. You're just asking for a total breakdown. Now, here's a super simple technique that makes a massive difference. It's called the move, then still technique. So why does this actually work? Well, when you first put the probe in and give it a little stir, you're making sure the whole surface of that glass bulb gets exposed to a fresh, uniform sample of your buffer. It's like wiping the slate clean. Then you hold it perfectly still. This lets all those ions settle down and properly interact with the gel layer without being all stirred up. It's such a tiny change to your routine, but believe me, you will get faster and way more reliable reading. And, this is where modern pH meters are just fantastic. They have features like Calamatic, which are basically designed to save you from yourself. The meter's actually smart enough to recognize which buffer you're using. So there's no way you can accidentally tell it you're calibrating with a pH 4 buffer when you're actually using a pH 7. It's just a simple but brilliant little feature that eliminates
one more huge source of human error. Okay, after you calibrate, you get to what I call the moment of truth, the slope check. Think of this as the final exam for your probe. If you get a slope between 98 and 102%, congratulations, your probe passes with flying colors, you're good to go. But if you see a number below 78%, that's a hard fail. This is a big flashing red light, a total stop sign. If you see that error, your probe is screaming at you that it's no longer reliable. If you decide to proceed with your experiment anyway, you're not doing science anymore. You're just making up bad data. All right, listen up, because if there's only one thing you remember from this entire explainer, I want it to be this. Are you ready? Never, ever, ever store your pH probe in distilled or deionized water. It is the absolute fastest way to kill it, period. Why? Well, it's just basic osmosis, right? The inside of your probe is filled with this very specific salt solution. When you stick it in pure water, all those essential salts start leaching out of the probe, trying to balance the concentration. You are literally bleeding the life out of your probe. You have to use the proper storage solution. It's specifically designed to keep the probe's internal chemistry perfectly happy and stable. Okay, but what happens if you inherit a probe that's, well, let's just say it's been abused? Or maybe your own probe is just getting old and sluggish. You're seeing that sad face pop up, your readings are drifting all over the place. Before you go and spend a bunch of money on a brand new one, hold on. There's a little rescue mission you can try first. It's a real expert-level technique, and honestly, it can work wonders. So, is your probe acting up? Is it sluggish? Are the readings drifting? Is that sad face mocking you? This is a super common problem, especially if you work with what we call dirty samples, things like cell cultures or protein solutions. What happens is they leave this invisible film of gunk all over the probe's glass bulb. It's kind of like trying to read a book through a really greasy window. But the good news is there's a way to clean that one. And here it is, the acid soak technique. It's a pretty simple 4-step process. First, you give the probe a gentle bath in some weak hydrochloric acid. This is what's going to dissolve that invisible film of protein gunk. Step 2, you rinse it off really, really well with distilled water. And then, and this is probably the most important step, you let it soak in its proper KCl storage solution for at least an hour. This lets it kind of recharge and re-equilibrate its internal chemistry. It's basically a spa day for your probe, and you'd be amazed what a difference it can make. So let's just wrap this all up. What's the expert's mindset? It's not about memorizing 100 different rules. It's simply about respecting the science behind the tool. It's about fundamentally understanding that you're not using a rugged thermometer, you're using a delicate, sensitive voltmeter. So what does that mean? It means you always calibrate correctly, and you always check that slope. It means you always use the move then still technique to get stable readings. And please, for the love of good science, never, ever store your probe in plain water. At the end of the day, the question you have to ask yourself every single time you go to take a reading is this: am I actually measuring reality, or am I just fooling myself with a number that just looks right?